Hello, and welcome to Learning from Nature, the biomimicry podcast with me, your host, Lily Ehrman. Wherever you're listening from today, thanks for choosing this podcast. We just hit over 10,000 downloads, and I truly cannot believe how much this space has grown in the last year and a half. I've been sitting on this interview for a few months, and I am so happy the time has come to publish because it's a juicy one. I speak with Raphael Kay about his research with organisms like squid and slime molds, and we journey into the super interesting strategies in nature that will have you hopping down lots of rabbit holes. Raphael Kay is a research fellow and incoming PhD candidate in the Biomineralization and Biomimetics Lab at Harvard University. He studies color change in marine organisms and network design in slime molds toward the engineering of zero-energy buildings and sustainable cities. Over the past 2 years, Raphael has led the development of a new type of energy-efficient building skin, leveraging not solids to manipulate incoming sunlight, but thin pouches of light-filtering liquids. This bio-inspired approach, taking cues from fish, squid, and chameleons, enables external facades to curate internal climates, providing a feasible path to net neutral responsive buildings. Raphael's liquid concept has been widely published and awarded. His original thesis was selected as the top dissertation in the mechanical engineering department at the University of Toronto, and multiple of his subsequent journal articles have been featured across 100 venues internationally, from scientific outlets like Nature to mainstream platforms like Bloomberg and Fast Company to educational handbooks like the Biomimicry Design Toolkit. For his work, Raphael also won more than a dozen fellowships and prizes in renewable energy and sustainability, including several of the most prestigious national scholarships offered to graduate students in Canada, while being named a Leader of Tomorrow by the international engineering company Soprema. Raphael was the Rhodes Scholarship and Knight Hennessy Scholarship finalist and has been a nominee for the Governor General's Silver and Gold Medals, Canada's highest academic honor in the undergraduate and graduate levels. Buckle up, this is going to be a good one.
Let's start by having you introduce yourself and kind of give us an overview of your current role and research focus.
Sure. So my name is Raphael Kay. I'm currently a research fellow, which basically just means doing research, not for a degree, at the Biomineralization and, of more relevance to this podcast, Biomimetics Lab at Harvard University. I work with Joanna Eisenberg, who is quite the influential figure in the world of bio-inspired biomimetic design and engineering. Before that, though, where I did actually the work that maybe we'll be mostly talking about today, I did a master's degree at the University of Toronto with a professor named Ben Hatton, and we spent quite a bit of time looking at some of the interesting ways that marine organisms can manipulate light and heat, and trying to see if any of those mechanisms were useful in our larger scale designs of buildings.
So I want to back up really quick and ask you how you first got interested in biology, and maybe even like leading us to like what drew you to study squid and these underwater mechanisms for optical change and modifying color and stuff underwater. But what got you started on this path in general?
Yeah, so I did an undergraduate degree in architecture, and I learned from some incredible people, but I will say, in general, I was a little bit put off by how much we, and when I say we, I guess I mean like the people teaching us how to design buildings in architecture school, how much we thought we knew about design, and how confident we were that we were the kind of be all and end all. And it's remarkable to me, actually, one of my original forays into this, like, we are not that good and we can learn from others that have been doing this for longer, was actually looking at, not in the context of buildings, but in the context of urban city planning. And I was looking at slime mold, which are these really cool, they're actually a single-celled organism, which is kind of mind-blowing. And they are really efficient at creating these network-like structures between a bunch of food sources. And there's been a lot of work, and we dabbled a little bit in this kind of body of research, but trying to translate some of the insights that they can offer into, connecting points, which is a problem we have as well if we're trying to connect, for example, railway stations and designing a city. And so, the kind of mind-blowing thing here is, like, they've been designing I'm doing like air quotations right now, but cities, so to speak, for something like 500 million years. And we have not been at it for that long. And, I'm not going to pretend like, if we give the job of city planner to one of these single cell organisms, they'll do a better job than we overall. But there are some key ideas and rules that I think were really exciting to study and to see the degree to which we can apply them in our own constructions. And so I would say in general in architecture school, architects are like, and I say this, I think I'm allowed to say this because I'm trained as one, but like I forget like the original, like Vitruvius, who was like one of the original architects. And the idea was like architects are like this Renaissance man idea that like architects can do everything. They're like, we're the best. And there was this incredible, I mean, in the core, it was human centric, right? It's like humans are amazing. And I was a little bit like, well, when I first came across these other kind of unique sources of inspiration, I was like, well, let's see what we can find here. And I had the amazing opportunity to work with Ben Hatton in material science in Toronto. And that's where all this kind of investigation came from. And his lab's a great place. If people doing totally random and different things. And that was exciting for me because I got to work with like, a brilliant mentor to me, Charlie Catrice, who was a physicist studying these random, patterns of fluids. And I was like, well, that kind of looks like what's happening in biology. Why? What can we put together? And it was this cool kind of, training ground to just like put a bunch of ideas together and see, I think I'm a little bit cautionary in how I talk about all this work because I don't want to pretend like everything we see in biology is obviously translatable. And so I think a lot of what we do is it's hypothesis based, right? It's like, are there things that we might be able to extract from these kind of, the natural organisms that we're studying that have been doing things for a long time and use them in a useful way. And I think scientific research is a great place to ask those initial questions. And I think I've gotten a great opportunity to do that with Ben in Toronto and now here in Joanna's lab at Harvard.
Okay, that led me to like 500 more questions for you because I'm obsessed with slime molds. And I feel like so many people don't understand slime molds and how cool they are and how weird they are. And I also just want to back up a second because you said something that I really want to emphasize. And that is, biology works, it functions in a certain way that's useful for that organism in its habitat, in its context, given its evolutionary timeline. It doesn't mean everything in biology and every strategy that we identify is going to be perfectly acceptable for the use that we want to translate it to in our design world. And that's important because I think we in biomimicry get this like headstrong viewpoint of like, I need to have one or two examples on nature and they are going to work really well. And then I'm going to translate them perfectly to my design. Done, hands are washed. That's the process. And it's so much more than that. And it's so much messier than that in a good way. Because one, organism that you're inspired by in nature or that you hear about, whether it be slime mold or squids, could have a really interesting strategy that could lead us to certain questions. And if you have a collaborative team, even better. You have your physicists, you have your architects, you have your biologists, and you can work on this project and everyone asks different questions. That doesn't mean that the strategy that you learn about is going to be the one that you end up mimicking or the one that's integrated into a design. It could lead you down a totally different path. And I just want to acknowledge that because I think it's an important part of biomimicry that's less talked about.
Yeah, I couldn't agree more. I mean, I know you had a bunch of questions. One thing I did want to actually maybe ask you, and I'm curious because it's in the name of your podcast, including the word mimicry. Something that I guess I maybe don't know how that term is often used. So I'm curious how you see it, because in our lab, where I was first trained by Ben Hatton, we almost learned of the word biomimicry as almost a bad word because we were like, well, there's so much fake kind of like there's so much sexiness around the idea of copying biology and like plastering the engineered world with biomimetic designs. And the reality is, like exactly like you said it, these are systems that were optimized for totally different goals and in different time frames. And that's not to say that there aren't examples that maybe actually perfectly mimicking the organism, especially formally, can be really useful. But I find that it's often dangerous to go about mimicking everything, as opposed to kind of with a little bit more nuance saying, okay, what is it that we actually think is useful here? And so I'm curious how you see the word biomimicry and like what it means.
That's a really good question. And I'm glad you asked that, because it's normally, I guess, not something that I would kind of bring in, but it is important. And I think that's very intentionally why I titled this podcast Learning from Nature as the title, and then subtitle bringing in the word biomimicry, because it can be a really controversial term, and it's a very complex term that implies a lot, and people have different feelings on it. And so the way that I see it, and the way that I've been trained, I did my master's in biomimicry at Arizona State University, which is one of the only masters in biomimicry created by Dana Baumeister, who I interviewed a couple of weeks ago and just published a podcast with her, who's a leader in this field. And she and her team and this global network of biomimics are really trying to rephrase this and create more of a structure to it, because one, we acknowledge it's an ancient practice. People have been learning from nature for millennia, right? I don't want to walk into this room and pretend like I'm the person that invented biomimicry or that the first person to learn from nature and apply it to design. That's just not the case. But in the last 30-ish years, there's been more of a process that's been outlined for academia, for research, for application, in a little bit more structured of a way to hopefully get at exactly what you're saying, rather than just, let's look at a leaf, it has a pretty shape, let's build a, car that looks like a leaf or that looks like a fish, but it doesn't actually function like the fish or like the leaf. And that's why in the practice of biomimicry, there's a lot of nuance and a lot of training around understanding your challenge, understanding the context of your challenge, understanding the audience of your challenge, understanding the place, the habitat, the ecosystem that your challenge will exist in. There's so much to it that can be really overwhelming. And I think it's overlooked when you hear a media article or a newspaper that has a headline about biomimicry. We're learning from peregrine falcons how to drop bombs faster. It's like, no. Or how to design fighter jets to, invade whatever country. For me, that is not biomimicry. They unfortunately, I think a lot of the funding for biomimicry in the past, there has been a big chunk in the military, which is an interesting conversation in itself. But there's a lot of applications in different spaces. And ultimately, when I talk about biomimicry, I mean people who are learning from nature, taking inspiration from nature, not using nature, so not bio-utilization or bioassistance, but they're learning from the mechanisms in nature that have a specific function and applying that to a design to make a life-friendly future. So I don't say sustainable, I don't say regenerative, because I think those fall flat a little. Life-friendly for me is the term I use when I say we need our design to exist in nature and not only take resources, but give back resources, not only be sitting in this habitat, but be giving back to the other organisms in this habitat, act as, a contributor to the ecosystem in whatever way that looks like. So it's a lot deeper and a lot more complex than I think we hear about on headlines. And that's why I started this podcast, to be honest.
Yeah, that's great. I appreciate it. I think it's a really exciting venture. And so I'm honored to be part of it.
Yay. All right. Are you ready to get into some optical mechanism stuff?
Yeah, let's do it.
I would love to ask you about slime molds too. Maybe that can be a separate conversation. But if we have time at the end, maybe I'll ask you some questions on slime mold, because personally, I'm very fascinated by slime molds.
Yeah, they're great. Yeah.
So, Raphael, can you explain the multi-layered optical mechanisms in nature that you talk about and did research in the publication that has been kind of highlighted in a lot of magazine articles recently? Multi-layered optofluidics for sustainable buildings. Maybe you can say that better 10 times fast.
Yeah, optofluidics. Sure. So I think nature. So the question you asked, I think the answer is kind of in the question you asked, like how does nature like control light with this multi-layered approach? And I think what's really critical, and it's like what I mean, a lot of people already know, but me entering this world more recently sort of found out and was really astounded by is, nature, and in my case, I'm looking more specifically in living organisms, so biology. with biology, it's very rare that there's an organism that does just one thing, uses just one mechanism to control light. And what's really beautiful is, 1 + 1 is greater than 2 often. And what I mean by that, you have one system in the skin, let's say, of certain organisms that does one thing to light, and you have one system or one layer beneath that skin that does something else. And when you combine those two mechanisms, it does something really beautiful. And so the example that we were quite fascinated by in organisms as we looked at a class of marine organisms called cephalopods. And so an octopus or a squid or a cuttlefish would fall in this category. And there are certain species of squid, for example, and if you look at their skin, they have a layer that basically does some color absorption. So they use these pigment containing sacs, and then they stretch those sacs to change their coverage over the area. And these are basically just color filters, and they do some absorption to change color. But then right underneath that, they have this secondary layer. And this layer is a totally different way of changing color. So the first way that I talked about, pigment-based, is where most of the color in the world comes from. You have an orange shirt, and the reason why it's orange is because there's an orange pigment. But beneath this layer of pigment-containing sacs in the organism, there is what we call a system that creates structural color. And what structural color is it actually has nothing to do with the color of the structure chemically, but there are actually physical or geometric properties that are small enough that they can actually manipulate light physically itself. So this is, light hitting the surface and bouncing off of it and interfering with itself in really interesting ways because of the actual geometry of the system. And that actually creates certain color. So it's a way of structurally creating color. And the beautiful thing in the squid is that you have a system of chemically creating color through absorption. And then right underneath it, you have a system of geometry for creating color. And you can basically use these synergistically. And synergistically is a word that I probably really overuse in the paper, but it's so key because these two mechanisms work sort of complementary to one another in creating really a sort of infinite library of optical responses. And in the case of the squid, these are really the people like to talk about chameleons as being good at changing color and doing cool things optically. The cephalopods in the ocean are really the kind of masters at camouflage and color change, and they can do all sorts of amazing things. And it's because they have this repertoire of possible states that they can achieve through this kind of chemical and geometric forms of manipulating light. And so in our case, the biological analogy is actually quite loose in that we're looking at kind of a multi-layered system that sort of has different ways of interfering with light to achieve a similarly versatile range of optical responses in buildings. And to give a little bit of context of why one might want to do this, buildings in the context of energy consumption and greenhouse gas emissions globally are, something, or perhaps the largest contributors to the kind of climate problem, in that they're consuming something like 40% of all the energy globally. Something like a quarter of the greenhouse gas emissions are dedicated to buildings. And a really big chunk of that is basically spent heating, cooling, and lighting buildings and building interiors. And so basically this comes down to indoor climate control. And it more specifically comes down to how can we better filter and manipulate incoming sunlight so that we ask our indoor heating, cooling, and lighting systems to do way less, thereby saving a ton of energy. And so the inspiration here in looking at these, incredible marine organisms that can really self-regulate and control sunlight adaptively was to, can we take these combination of the sort of multiplied chemistry plus geometry system, apply that in a window, and potentially save large fractions of energy. And so in our case, we use liquids because liquids are a great platform to kind of do whatever you want. You can put a particle in them, you can put a molecule in them, and you can achieve this kind of biologically analogous sort of library of optical responses. And in our models, we found that this type of system can save something like 40% of the energy that, comparing it to sort of the state of the art in kind of dynamic shading technologies, 40% more energy on heating, cooling, and lighting, which is really exciting for us. And it kind of means that it's possible that this kind of bio-inspired liquid approach to climate control, could could play a role towards our ultimate goal and kind of zero energy, zero carbon building.
And I recommend folks read this. It's like such a well-written paper, and I got so curious about so many different things while reading this. Again, it's called Multi-Layered Optofluidics for Sustainable Buildings, and some really great graphics, some really great explanations. I'm gonna back you up a tiny bit because I did have a question, and actually it speaks to what you mentioned, like this kind of weird pathway to biomimicry. It's not always exactly what happens in nature, but are there aspects of thermoregulation for this mechanism in nature, kind of multi-layered, multiple photonic layers that actually have a functional purpose for thermoregulation, or is that just kind of the application side?
I mean, actually going to so chameleons do something interesting where they have two overlapping layers, and each of these layers has a bunch of kind of tiny nanoscale structures that can reflect near infrared sunlight, which is basically invisible heat.
Okay.
You can think about it. And so this is an example of where one layer can do something more along the lines of changing color, but another layer can reflect heat. So they have each layer doing something different. One kind of approaches color, one approaches the need to sort of thermoregulate.
Okay.
Yeah, I mean, there's all kinds of loose analogies all over. I mean, one of our other papers, which is probably a little bit more of like a palatable, like direct bio-inspired system. We did some work where we looked at decapods, which are crabs or krill, and they have this really cool system where they basically spread pigments within a branching cell, and they can push pigment out to cover their skin, and they can bring it back together in a central container. And we looked at this mechanism, and we proposed something analogous for a building skin. And the crabs, for example, use this system to dynamically thermoregulate because these pigments can basically block solar heat. So they use it, at times when they want to cool, they spread those pigment cells sort of throughout the container, so to speak, and they bring it back in, and we did something similar. So I think the answer to the question loosely is like, yes, there's all sorts of related ideas. I think we've been very careful, I guess, and like and loose even in I mean, I guess those words are kind of conflicting, but we've been loose in our bio inspiration. I guess we've said,
right.
It is only these things I think might be relevant in buildings. So we've been careful to only take certain elements. But I think the idea of multiple layers doing multiple things functionally is such a simple and prevalent idea across biology, but it's such a beautiful idea. And I think it could really change our outlook of how we design smarter engineered structures like buildings.
So true. And this is why I love biomimicry and folks like you and researchers who are kind of combining fields and doing some cross-disciplinary stuff, because it leads you and others to more questions. It's like, well, does it do this? Let's look into this more. And like you said, there's this beautiful simplicity in nature that is, maybe there's multiple layers that are really simple, but, added together, they have this very useful function. They have many useful functions. It's so cool. I could go down this rabbit hole for a long time.
Yeah. I mean, it's basically what I do. I try and study the multi-layered systems and see how they might be useful otherwise. Yeah.
And you might not be the person to answer this, but I threw in this question because I teach a class called Biology for Biomimicry, and we do talk a little bit about this idea of squid and cephalopods like changing color and explaining the mechanism used to do that. Is it centralized? Is it decentralized? Do they do this involuntarily, or is it kind of like a nervous system control, like I would assume, or is it kind of like somebody explained it like breathing is for us, which seems pretty wild to me.
Yeah. So I am not the best person to answer this, but I'm going to take a stab at it anyways, because
cool.
it's a great, it's like the answer to this. I know the answer. I'm not the person to give it, but and I'm going to screw it up. But I saw a TED talk by a guy named Roger Hanlon who has done some amazing work on understanding how cephalopods change color, and his response to this would just be brilliant. But I'm going to give it a go, and it's amazing because I think these numbers are going to be off, but so I'm not going to give any numbers, but a disproportional percentage of the neurons in a cephalopod, like an octopus, are along the skin of the organism. So in humans, a large fraction of our neurons happen to be centralized in our brain. on these cephalopods, they're actually largely along the skin. And that gives, you can almost say that their brain is along their skin, which is a very useful thing for control. And so that, they have a couple different systems. All of them are sort of, some of them are sort of neuromuscularly controlled. So from like a centralized nervous system. There's other organisms that use kind of hormonal effects to change pigments. So there's not one overarching answer for all these, but I think a beautiful takeaway is that like this level of, you can think about it as sort of decentralized control, because all these neurons are basically distributed so well across the body itself that it enables this amazingly rapid, control of color right at the interface. And I think in the context of buildings, we actually have a very similar problem where it's like, we make all of our decisions internally, and we have all of our control internally. All of our heating, cooling, lighting is done internally. And if we shift our mindset to kind of the way a lot of these organisms work, where most of their control is right along their skin, it's kind of like it's a lot more efficient to control the environments right at the kind of point of contact with the environment than it is to let too much in and then have to overcompensate for it, basically. And so I think it's a beautiful analogy to kind of compare the general control strategy of these organisms, basically moving from a decentralized control model, having a central brain, to sort of a distributed brain across their skin. And I think that's ultimately one of our goals in these kind of building skins, where we ultimately want to have this kind of distributed digital control of fluidics right along the window interface to control light and heat in intelligent ways right at the interface.
Not requiring a lot of extra energy to be pumping stuff around or reacting and then sending a signal and then receiving a signal and then taking action. That's so cool.
Yeah, exactly. Having it sort of right at the point of contact.
So something that came up, and this is, I think, a good segue to kind of talk more about this building application. I have a total lack of knowledge about like heat transfer and how it relates to like this challenge of building energy use. Can you maybe give us some explanation around the different types of heat transfer and how they relate to a building's energy efficiency?
Yeah, I mean, so fundamentally, like in terms of a building, the idea of a building is generally to keep the inhabitants comfortable. And so to do that, you sort of want to maintain a steady state of like, enough illumination to see and a, comfortable temperature to, exist within. And so to do that, usually we rely on electric lights often to keep us well illuminated, and we rely on heating and cooling systems to kind of tune the temperature environment. And there's definitely an old school paradigm in building design, which is like the outdoor environment is not our friend. We're going to insulate our buildings as much as possible. We're going to keep the outside, and we are going to kind of make a utopia on the inside. And it's a beautiful way of thinking if you have infinite energy, but it doesn't really take advantage of one of our most kind of available and exciting resources in sort of the environmental temperature field and solar field. And so, for example, the mode of heat transfer that we're particularly interested is radiation. And so sunlight comes in various packages. It gives us illumination in the visible spectrum, but it also gives us heat. And how it gives us heat is that it comes, these sort of packages of sunlight come in all different spectrum, and we as humans will absorb those frequencies, and that absorption will basically turn into heat. And so all the objects in our room, especially the darker carpets or whatever it may be, will absorb that sunlight and convert it to heat. And so solar absorption is a great source of thermal energy and heat, basically. And so if you can, and yeah, honestly, I'm going to get maybe a little bit into the technical detail because I think it's so exciting. One of the grand challenge that our research group has been trying to solve, and I hope we've gotten mostly there by truly with bio-inspired design, is the idea that if we can beautifully take advantage of sunlight in that we can control where it goes within a room, we can control where the heat goes, where the light goes, how much heat goes over here, how much light goes over there, and really be able to take advantage of the incoming energy available to us, we really won't need to rely on heaters and coolers and even electric lights to the same degree. And so practically speaking, for example, if a ray of sunlight hits your window and you're able to take that ray and spread it deep into a space within a room, you will no longer need to have an electric light source illuminating the back of your room, because you have daylight that is actually somehow spread from the window all the way into the back of your room. And so that's one cool thing that could save energy. Another thing is, when it's really cold out, you want to be able to basically take all the available solar heat and bring that inside. And, vice versa, when it's really hot out, you want to block all the heat you can, but still let in some light. And so they're very complex things. And most of the systems we've built today, I'm looking at my window right now, we have some shades, and they're incredibly single functional, monofunctional, right? They can block everything or nothing type of thing. And so really one of the grand challenges in building design is, can we develop a window that can universally control sunlight? And what this means is, can it be able to independently control the intensity of a beam of sunlight, the direction of the beam of sunlight once it's transmitted, and the color of a beam of sunlight? And the reason why color is important is because color is not just sort of when we see green or blue or yellow, but it's also the invisible colors. And so if we can control if some visible light comes in so that we can see, but not letting in the invisible heat, that's actually really useful. Think about, the middle of a summer day. You don't want to use electric light. So you want to bring in the sunlight for the visual part, but you want to block as much heat as possible. And so being able to control the color, i.e. bringing in the daylight, but not the, infrared heat, is another critical function. And so we've been working towards this universal solar control window, which is kind of what this, optofluidic paper approaches. And we actually have an upcoming paper that I think fully achieves that, basically by looking at the squid mechanism of using both pigment and geometry to control light. And we're basically able to take a ray of sunlight. We can say, okay, we want it in the back of the room. We want a little bit in the front of the room. We just want the visible wavelengths, not the infrared wavelengths. And we want to dim it a little bit because it's a little bit too intense. So we can control the intensity, the direction, and the color all simultaneously, which is, and according to preliminary models, possible to save, about half the energy that, we're consuming in several types of indoor environments, which is super exciting. And so that wasn't at all the question you asked about heat transfer, but hopefully it
got there. Yeah, and that spurs so many other questions, but I guess I'd like for you to go into a little bit more depth on like what does this window look like that you're talking about, that was inspired by the squid, that you're maybe taking this next step? Like what does it look like? How does it work?
Yeah, so actually the origin of the design, even though it's building on all these exciting optical systems that we find in the squid and other marine cephalopods, is actually a totally different source of bio-inspiration. This project actually started with my supervisor, Ben Hatton in Toronto's work looking at mammal-inspired heat control. So if you are somewhat familiar with what our veins do in our skin, they can dilate and they can basically move their relative position or relative size compared to the skin interface, so that they can basically control if more or less blood is flowing directly along the skin. More flow along the skin would lead to more cooling, less flow along the skin would lead to less cooling. And it's a dynamic heat management tool that a lot of mammals employ along their skin, this idea to kind of flow fluids in vein-like structures along the surface. And that actually inspired some of his work, which is a beautiful and perhaps a little more direct biological analogy for controlling heat in windows. You can imagine a bunch of veins in windows, and these veins can carry liquids that will absorb sunlight. Even water does a great job of absorbing invisible infrared as they flow, capturing a bunch of the heat of sunlight and then carrying it away. So in the summer, you can save a ton of energy if you have these vein-like mammal-inspired windows. And so that was the original idea, to have these sort of vein-like, fluid-like windows. And we decided to look at, that was sort of controlling heat, But we decided to look at how some of these marine organisms control light, because another big part of the energy equation in buildings is sunlight, and actually sunlight directly leads to heating and cooling. So it's, even saying light is not the full story. It's really heat and light, but using optical mechanisms. And so we sort of took the existing architecture, which was this kind of vein-like fluidic window, and we decided to put all types of different liquids that were capable of, for example, blocking just the invisible sunlight, but letting the visible sunlight come through. Or, for example, scattering light to the depths of the room, those types of things. And so if you can imagine, you have sort of 3 layers in a row. The first layer is able to control the intensity of sunlight with sort of a darkening like liquid. The second layer is able to just control the absorption of invisible heat without affecting visible light. Through it looks clear to us, but it does a lot of absorption in the invisible. And then there's a third third liquid in these vein-like structures that basically controls the scattering. So we have a lot of nanoscale particles that can basically manipulate light to send it to the back of a room. And so these are these kind of sequential microfluidic window layers, if you will, and put it all together, you kind of have this kind of tri-layered fluid system. And you can design the veins in a whole bunch of ways. You can look to biology to get interesting forms for how the veins might be most optimized for kind of overall coverage. Biology does a really good job of creating some nice optimized structures to do that. But we were even looking at simpler structures that do still quite a sufficient job. And so practically speaking, we're really talking about liquid windows in which different liquids can be digitally controlled. And every time I bring this up, people go, "Wow, so you're spending energy to sort of pump liquids?" And the answer is, for now we are, but sort of our models are telling us we're spending about 1/200th of the amount of energy we're saving and pumping. And so it's quite a negligible impact. And I think we also are trying to find ways to do this all passively. We can use some of the interesting properties of liquids, their temperature dependence, to make them kind of flow themselves, these types of systems. But the reality is, I don't think it's worth getting too caught up on the fact that we're using energy when we're saving 200 times as much energy. And so I think for us, it's a really exciting leap forward. But to answer your question, practically, we're basically talking about a bunch of vein-like liquid windows.
So interesting, especially because as I'm looking out the window right now in my office, and it's something at least I don't normally think about. And it's such a portal to wasted energy or excess energy. Like, my office gets terrible heat. I don't get enough sunlight in here. I have to just pump a bunch of heat in here. And then I'm sure it's just going straight out through these windows that have a metal outer edge. So much potential here. Super cool.
Yeah,
so
exactly.
One of my kind of last, at least, I don't want to say last questions, but one of my last questions is kind of taking this to the next step. If funding and market issues, market integration was not really a factor, how would you implement this technology to allow for the greatest impact? You could also see this as is there a next step for this design?
Yeah. Yes, there absolutely is. So the short-term plan, I'm not sure if this is the best plan, but it's the one we're going with, actually, is so this work was started in Toronto with Ben Hatton. I'm currently at Harvard with Joanna Eisenberg. We are now sort of operating with these kind of 2 parallel tracks, where Ben and Toronto is working on taking the stuff we've shown and basically engineering it better. How can we actually apply this to a building to sort of convince the industry that it's worth putting these on buildings, and make it a little bit simpler, make it a little bit more scalable, the kind of big engineering questions. I maybe this is the exact opposite, but I think it's equally as exciting and worth doing. Is I'm actually trying to see what other functionalities can this window do on the optical and thermal side. And so in some ways we're going in the opposite directions. They're trying to simplify the engineering to scale up, and I'm trying to ask the question of, can we make this, in my opinion, already pretty cool system do even more things? So can it also simultaneously control another way of moving heat, which is sort of through conduction and convection? Can we actually used the word portal earlier. Can we actually make this a switchable portal to transfer heat? There are times when you will accidentally let too much heat in, and it would be beneficial to let that heat flow out. And so you can sort of switchably open and close that portal. And there are other times, for example, on a winter day where your window will absorb a lot of sunlight and it'll get really, really hot, but then it'll end up losing all that sunlight because your window is so well insulating that none of that heat will end up coming indoors when you would want it. And so how do we actually optimize the thermal transfer and the optical properties, synergistically again? Those are the questions I'm thinking about. So I'm trying to make this like the best, coolest functional thing we can imagine. And I think the rest of the team is working on scaling up. And I think there are areas where we'll probably, information from the engineering side will inform our side, and new insights from our side can inform the engineering side. And so, we like to throw around numbers of like 1-2 years, whatever. I don't think anyone really knows. We're all really driven to make this, go to market and actually see the kind of impact of this kind of bio-inspired design at a larger scale. And so that's sort of central in our mind. I can't really give a better answer in terms of like timeline and next steps other than like we're working hard in the lab, but we definitely are driven to make this a reality.
I like what you said about just adding more functionality. And I feel like that, well, it could be adding obviously a lot of complexity, but it also could be adding a lot of value. Sign me up for when you're selling these. I want one. Yeah, there's just so much opportunity here because, like you mentioned at the beginning, our buildings are a huge consumer of energy, one of the top consumers of the energy globally, which is obvious when you think about it, because we spend so much of our lives in buildings, working in buildings, housing stuff, storing stuff, building stuff, whatever, all happens inside. And there's just a lot of wasted opportunity, wasted energy, wasted heat. And then we're just compensating for that with pumps and energy use, coming from fossil fuels. So yeah, this is super hopeful, and I'm really excited, especially because it sounds like it's a very collaborative effort, which I think is, something I want to note in this podcast. These collaborations are what make something like this possible. When people reach across departments and reach across fields and get excited about something in biology, bring in the biologists, bring in the architects, and bring in the physicists, there's just a lot of potential there.
Oh yeah. Like I can't emphasize enough how useless I would have been in this effort by myself. Like I think it is truly like, people love to say that collaboration's cool, but like this is like actually like nothing would have happened without the collaboration. And it's just different people coming with weird ideas from different perspectives is such a cool thing. I think it really leads to exciting, avenues. But yeah, I mean, I think I think I've said this a couple of times already, but like to reemphasize this idea of like, kind of like bioinspiration at different scales. And like we were looking at bioinspiration from like a sort of systems perspective, of like how these mechanisms work optically or thermally, which is cool. But I think another biological analogy we've tried to kind of follow in our work is just the general idea of like how organisms control light and heat. And oftentimes it's sort of, instead of a centralized mode of, having the fan run extra on the inside because they didn't do a good job of controlling their skin, like all the control really is done at their skin. We humans, like you can look at your veins and how they control heat. You can look at all these amazing, color changing chameleons and fish and squid and, crab. And they do this for, sometimes for communication reasons, sometimes for mating, etc. But a lot of it is to basically, efficiently shade, like, the krill is an example we use when we did a krill inspired project about a year ago that also got some nice attention. And that was, the krill use it basically to shade themselves from the sun, which is like the exact problem we have sometimes. And, crabs, do it to control, thermal heat gain, and squids do it to change color in all cool ways and to manipulate the direction of light, which is something we need to do if we want to save energy. And like doing things on the skin of buildings, like thinking of buildings as having a skin. Like I like using the word skin because it's like, that is literally what we need. This kind of dynamic skin is such a great kind of way to think about how we should design the next generation of kind of hopefully low carbon, if not zero carbon, zero energy buildings.
It's funny because it's kind of full circle. I interviewed Dana Baumeister a couple weeks ago, and she was talking about how she got into biomimicry. She was trying to write her master's thesis and do a project on creating a building exterior that functioned like skin, a building skin. And this was, in the 90s, the early mid 90s, late 90s. And she couldn't find the right department. Like nobody was doing this at the time. And so she eventually found Janine Benyus's book and met with Janine Benyus, and then they collectively started the Biomimicry Institute and the consulting firm, and it just blossomed from there. But yeah, it's like this curiosity, this inquiry building of like, okay, we know that nature does this well, really well, multifunctional, it's simple, it's genius, it's effective. And some of the stuff we do is just the opposite of that. How do we start integrating, even if it's just bits and pieces, these strategies from, very specific functions in nature into the same functions that we want to accomplish in the built environment? So super exciting.
Yeah. I think, one of the exciting, I don't think I think this is takes a layer of thinking to see that it's a good thing, but so when, we're writing these papers and so for this recent paper, this multi-layered optofluidics paper, we were kind of playing around with the title, and we were thinking about using, the word bio-inspired or squid inspired somewhere. And we actually ended up not doing that. And one of the silly things we were thinking about as a reason not to is that it's actually overused, which I think is an amazing thing. I think you've seen in the last 10, 15 years, so much research in the literature popping up in bio-inspired. And before we were talking about how it can be overused in a bad way. Here, purely in an incredible way, you see in the last, I'm only, 24, so I can't speak to much more, but even in the last, when I've been a researcher in the last kind of 4 or 5 years in the academic world, how much ideation there is, and from a bio-inspired lens, it's actually phenomenal that it's not even cool anymore to be naming your papers bio-inspired, because it's so well understood that biology is an incredible source of inspiration. So I think, in the academic world, I'm not sure Dana would have had those problems like today in kind of the engineering labs that I'm in. It's such a well understood standard for, if you want to look for a good idea, start with the kind of master designer in nature. She's been doing it for a lot longer than we have, right? So
yeah,
that's I think super exciting.
Yeah, and gives me a lot of hope, because I'm relatively young in this space and have only been in love with and kind of practicing biomimicry for less than 10 years, but in that time it's just exploded and become a little bit more well understood. I think we still have a long way to go as far as, like I said earlier, the kind of this deeper biomimicry of okay, we're understanding something from nature, how do we implement it into a life-friendly design that actually functions like the natural world? But it is happening. You're doing it. There's people out there that are doing that, and it's really exciting. So my last question. Go ahead.
I was just gonna say that I think one of the what I think from my view, we're talking about all these functional goals of doing things to manipulate light and heat, and we're trying to get the kind of output performance, and that's one of the big parts of this building energy equation. We can get pretty far with bio-inspired approaches. I think the other side of it that I know nothing about in terms of solving this problem, but is worth acknowledging, it's also a big part of it, is the actual materials we use, not in terms of their functional energetic output, but actually the energy that goes into making them. And I think that's the other side of this building sector equation, where it's we do all this cool stuff with light and heat, and we I think do a pretty good job. We're mostly using water actually, and we have some particles, and that the water can be put between panes of glass or plastic, whatever it is. It's a pretty general idea, so it can be applied to all kinds of sustainable material practices, but there just aren't many of them today. So it's even in our lab, all our proof of concepts are with plastic or with whatever we have around. It's if bioplastics or if whatever it was more of a thing, we could really kind of access the next level, because the mechanisms we're talking about are quite general to the material palette that we'd have available. And so I think there's an equally exciting world of kind of discovery on the other end of embodied energy materials, and once we can put these together, that's when I think we'll really make some pretty exciting impact.
I'm really glad you mentioned that. I think it's a really good thing to think about and have conversations about, because it's the materials we have right now to build this kind of technology is very limited. And when we start thinking about life cycle analysis, what goes in to make it, where it goes at the end of its life cycle, does it sit in a landfill? Can it be recycled? Can it be reused or upcycled? we really start bringing into this like really deep biomimicry conversation. Is this life friendly from beginning to end, or is it circular? Like all of these questions start to come up, and I'm hopeful. I'm seeing some more material stuff come out, but it might be a while. And that's where I love that you mentioned this kind of general idea that can be applied or built with different technologies once they're more available.
Yeah. And I mean, I love being in the research world. I mean, maybe it's like partially like a mentally sheltering thing, but I think it's true in that like we are all incredibly optimistic because we need to be. It's our job to kind of be excited, right, about like all the things we're doing. And I think like, like I like you read the news, you read all these people like, talking about like the doomsday thing with climate, and it's like it's nice to be in a world where it's just like all the problems that we have regarding climate, we actually look at as positive, kind of, this is an opportunity to do some really exciting stuff, challenges. And so, I can acknowledge the potential, like, disastrous mindset that can come of this. But I will say that like in this world of, and I'm not sure how it translates to like in the education world of biomimicry, but at least in the academic research setting, in the material science labs, whatever, I think people are super optimistic and excited about what we can do with regards to the climate.
And to a certain degree, we have to be hopeful. I mean, that's why I love biomimicry, because it does bring in so much more hope and kind of this humbling aspect of like, we don't have to solve everything. Sure, we have to build it. We have to create it. We have to at least quiet our cleverness enough to like learn from nature and have that kind of humble approach. But there are a lot of solutions out there already that we can mimic and build into our designs to make them super efficient, that have been tested for 3.8 billion years, or hundreds of million, however long that organism has been adapting and fine-tuning its mechanism. We can tap into that, and that act of like tapping into this genius in nature is what grounds me and hope and brings me hope in biomimicry.
Yeah, me too, definitely.
And you kind of already answered this, but my last question for you is just like, what are you excited about next?
I don't know. I mean, I don't have an answer because there's so many things. Like I think on the one hand, I mean, this is like goes way beyond the idea of biomimicry. It's more of like a deep question I need to figure out for myself. But in terms of impact, but it's like we've done some cool things, I hope, with some of the systems that we've tried to introduce. And I'm kind of reaching this crossroads where it's like, we're potentially talking to people in industry, whatever. It's like, do I dedicate more of my time to scaling up this system that we've kind of come across and try and actually make that a reality in the real world and big scale? Or do I spend more of my time doing what I've kind of spent the last 4 years doing that I absolutely love, which is like playing around with these biological ideas and seeing what proof of concepts we can demonstrate? And so I think it'll be this like challenging, like interpersonal thing for me, which is like, where is there the most impact to be made in terms of like, because I think in general, people in research have this kind of conflicting thing all the time where it's like they love what they do, they love kind of playing in the sand with these interesting ideas. There's a ton of value there. They can publish a very nice paper that proves something out, but are they going to then take that next leap to actually make it in the try and scale it up, or do they have more value kind of proving out other ideas, searching for other biological solutions, for example, to problems in buildings? So for me, I'm trying to find that line right now where it's like, what percent of my time do I dedicate to continuing to explore this biological inspired space? What other, there's an infinite library of other ideas to tap into. Or do I kind of stop myself for a second and go, okay, actually, maybe I can make this on, your window in 4 years, and is that of more value to society? So a combination of those two, I think, is where I see myself next.
Yeah, that's not a light thing
No.
to figure out for sure. It's a bit of a heavy conversation, and it's so true. I was at that crossroads a couple of years ago myself, and it was like, okay, I'm excited about this. What do I do to create the most impact, or that feels to me like the most true? And education was definitely that space, but I was super tempted by this idea of like the startup culture, creating products and getting them to market. And then I was like not even a year in that field, I was like, oh no, this is not where I want to be. But it's so true. It's like, you have to, one, research it and get excited about it and put it out in the world. But then if you're excited about it enough, like you do want to see it to the next step, or hopefully somebody maybe comes in and starts talking about how they can do that with you. So a lot of potential, which is exciting, like you said at the beginning, but also kind of terrifying.
Yep, exactly. But I think that's a good thing. Keeps you, ready for the next day.
Yeah. And I'm hopeful. I feel like, there's a lot of people out there who are ready to provide funding, ready to kind of create this team and create these companies that are looking to nature and applying them in design, because it is a very hot topic right now and there's a lot of potential. So I'm hopeful that you'll figure that out and that'll happen well for you.
I think there is a lot of funding in the space, which is super motivating as a researcher, because a lot of research is kind of like scrapping for money. So it's really nice to be in an area that, like, maybe we're not at like whatever it was, like 1 billion or 2 billion biomimics yet, but we're there's momentum, I would say, which is super cool.
Yeah, and we just need folks maybe not even doing biomimicry 100%, biomimicry the whole way. Maybe they're bio-inspired, maybe it's a little bio-utilization, bio-assistance, using the natural world and acknowledging that the natural world is a place we can get information and that we are part of, and that we need to ensure it's around and protect it and acknowledge that we're part of it.
Yeah, absolutely.
Raphael, thank you so much for joining me. This was a joy, and I feel like I learned so much, and I'm going to go down 500 more rabbit holes learning about some of these color strategies in nature.
Yeah, thank you so much for having me, Lily. I also really enjoyed it, and yeah, looking forward to seeing where the podcast goes.
If you've made it this far, I applaud you. I couldn't bring myself to cut any of that conversation shorter. Now, let's go look at squids in the aquarium and marvel at all the cool stuff we see along summer hikes. This is your monthly reminder that our natural world is truly marvelous. We just need to make time to listen and learn.